I'm sure most of you have heard of Pascal's triangle. This array of numbers where each entry is the sum of the two numbers above it. There are many papers, articles and videos that explain in depth the patterns and complexities of Pascal's triangle. But in this video, we're going to take Pascal's triangle and expand it into 3 dimensions. And to help with visualization, I'll be showing it layer by layer, like I am on the right here. So without further ado, let's get exploring Pascal's tetrahedron. Pascal's tetrahedron is an array of numbers where each number is the sum of the 3 numbers above it. For example, this 6 is equal to the sum of the 3 2's above it. And this 12 is equal to the sum of the 6, 3 and 3 above it. We have to be careful though. Unlike in Pascal's triangle, not all sets of 3 adjacent numbers will produce a number that's actually in the layer below it. When Pascal's tetrahedron is displayed like this, 3 adjacent numbers that form a triangle pointing downwards do in fact produce a number on the layer below, but 3 adjacent numbers forming a triangle pointing upwards don't. Let's briefly return to Pascal's triangle and look at a couple of functions that produce its numbers. The most common of which is the choose function, where a choose b is defined as a factorial divided by b factorial times a minus b factorial. For example, 7 choose 3 is equal to 7 factorial divided by 3 factorial times 7 minus 3 factorial, which is 7 factorial divided by 3 factorial times 4 factorial, which is 5040 divided by 6 times 24, which is 35. Now, starting from the top one, we can drop down into the left 7 times and then go across to the right 3 times. Here we'll find 35, which is 7 choose 3. Another function we could use is defined as f of ab is equal to a plus b factorial divided by a factorial times b factorial. For example, f of 3, 4 is equal to 3 plus 4 factorial divided by 3 factorial times 4 factorial, which is equal to 7 factorial divided by 3 factorial times 4 factorial, which is 5040 divided by 6 times 24, which is equal to 35. And starting from that top one, we can go down into the left 3 times and then down into the right 4 times, and we'll find 35, which is equal to f of 3, 4. From this point, we'll continue using the second function. From this 35 we found, if we count how many steps to the right, we get 3, which is equal to our value for a. And counting the steps to the left, we get 4, which is our value for b. This will be the case in general. For any number, its distance from the boundary on the right will be a, and its distance from the boundary on the left will be b, and said number will be equal to f of a, b. This concept of looking at a number's distance from the boundary will be useful later. Now, we are going to define a new function, g of a, b, c, which is defined as a plus b plus c factorial divided by a factorial times b factorial times c factorial. This function looks very similar to the f function we had for analysing Pascal's triangle, but let's see if it actually produces the numbers in Pascal's tetrahedron. Here we have the 4th layer of Pascal's tetrahedron with the borders drawn on for clarity. Looking at this 12 here, we see that its distance from the bottom border is 2, its distance from the right border is 1, and its distance from the left border is 1. Using these numbers as a, b and c, we get that g of 2, 1, 1 is equal to 2 plus 1 factorial divided by 2 factorial times 1 factorial times 1 factorial, which is 4 factorial divided by 2 factorial times 1 factorial times 1 factorial, which is 24 divided by 2 times 1 times 1, which is indeed 12. Now we are going to show that 3 adjacent numbers from this function do indeed sum to the number below them. To do this, we will first write out g of a minus 1 bc, g of a b minus 1 c, and g of a b c minus 1. Then we will sum them all up. Factoring out a common term, we get that their sum is equal to a plus b plus c minus 1 factorial times 1 over a minus 1 factorial times b factorial times c factorial plus 1 over a factorial times b minus 1 factorial times c factorial plus 1 over a factorial times b factorial times c minus 1 factorial. This is equal to a plus b plus c minus 1 factorial times a over a factorial times b factorial times c factorial plus b over a factorial times b factorial times c factorial plus c over a factorial times b factorial times c factorial. This is equal to a plus b plus c minus 1 factorial times a plus b plus c all over a factorial times b factorial times c factorial. And by definition of factorials, this is equal to a plus b plus c factorial over a factorial times b factorial times c factorial, which is exactly g of a, b, c, showing that if three adjacent numbers on Pascal's tetrahedron line up with this function, then so does the number below them. Here are the first three layers of Pascal's tetrahedron. By fairly simple calculation, we can see that g of 0, 0, 0 equals 1. And g of 1, 0, 0 equals g of 0, 1, 0 equals g of 0, 0, 1, which also equals 1. Thus, the first two layers perfectly line up with our g function. And since we showed earlier that if we have a triangle of entries that follow our g function, then the number below them will also follow the g function, which means that if an entire layer follows our g function, so will the entire layer below it, while also using the logic from Pascal's triangle that any number on the boundary will have a phantom zero as one of its parents. Briefly looking back at Pascal's triangle, one such use we have of this is that it perfectly gives the coefficients of the binomial expansion, meaning that if we take a plus b and raise it to some power n, the coefficients we get out of that perfectly line up with the nth row of Pascal's triangle. Likewise, each layer of Pascal's tetrahedron gives us the coefficients of the trinomial expansion, meaning that if we take a plus b plus c and raise that to some power n, looking at the nth layer of Pascal's tetrahedron, we find its coefficients. For a proof of the binomial case in Pascal's triangle, let's look at the coefficients of a plus b to some power n, and let's say that the coefficients of a to the s minus 1 b to the t and a to the s b to the t minus 1 do in fact line up with Pascal's triangle. Now let's see the coefficients of a plus b to the n plus 1, which is equal to a plus b times a plus b to the n, which is a times a plus b to the n plus b times a plus b to the n, which will give us a times f of s minus 1 t times a to the s minus 1 b to the t plus many other terms, plus b times f of s t minus 1 times a to the s b to the t minus 1 plus many other terms, which will equal f of s minus 1 t times a to the s b to the t plus f of s t minus 1 a to the s b to the t plus many other terms. And combining like terms will give us f of s minus 1 t plus f of s t minus 1 all times a to the s b to the t plus many other terms. Now, one of the identities of the f function is that f of s minus 1 t plus f of s t minus 1 equals f of s t. Using this identity, we see that the coefficient of our a to the s b to the t term is f of s t, showing that if the coefficients of two adjacent terms in the expansion of a plus b to the n line up with Pascal's triangle, then so does the corresponding term in the expansion of a plus b to the n plus 1. And if all the coefficients of the expansion of a plus b to the n lines up with Pascal's triangle, then so will all the coefficients of the expansion of a plus b to the n plus 1. And previously, we showed that it does in fact line up for all n up to 5, and therefore by induction continues forever. Now, to prove that the coefficients of the trinomial expansion line up perfectly with Pascal's tetrahedron uses almost exactly the same logic as we just used. Now, I won't go through the proof line by line like I did for the binomial expansion, because it'll be very tedious. But just know that it is also a proof by induction, and since we showed that it is true for the cases of n equals 0 and n equals 1, the induction carries forwards to all n. Pascal's tetrahedron, like Pascal's triangle, has many strange and wonderful patterns in it. For instance, every third layer has one number in the middle that is surrounded by 6 identical numbers, and the ratios of the center number to the surrounding number follows a predictable pattern. But now I want to finish showing off one of my favourite patterns in Pascal's tetrahedron, because it's a pattern that relates to Pascal's triangle. Here we will show the first few layers of Pascal's tetrahedron alongside cut-offs of Pascal's triangle of the same size. Comparing a line of a layer of Pascal's tetrahedron to the corresponding line of Pascal's triangle, we can see it's just a straight multiple of the entire line. Moreover, for each layer, the pattern of multiplication lines up perfectly with the cut-off row of Pascal's triangle. To accurately describe what's going on here, we'll pick a pair of corresponding numbers, such as 3 and 12 here. We can see that this 3 is 3 rows down from the top. And starting on the bottom row, going 3 steps to the right, we reach 4. And 3 times 4 equals 12. For a second example, we can look at the 2 and 20. The 2 is 2 rows down from the top. So if we go 2 steps along from the bottom, we reach 10. And 2 times 10 equals 20. Now let's look at this phenomenon in a more general way. Let's say that our cutoff row is x rows down from the top, and that our selected number is y rows down from the top. This would suggest that we can find our multiplier by going y steps along the bottom row. Note that when we draw a line from the start of the bottom row to the top one, and another line from our multiplier to the end of our selected row, that these two lines are parallel. This would indicate that our selected row has a total of y steps from end to end. Let's say that our selected number is a steps from the left and b steps from the right. We see that y is equal to a plus b. Also note that our chosen value is equal to f of ab, and that our multiplier is equal to x choose y, which is equal to x choose a plus b. We can also see that the corresponding value to our chosen value in Pascal's tetrahedron is a steps from the left border, b steps from the right border, and c steps from the bottom border. Thus, it is equal to g of a, b, c. Also note that our chosen value is c steps from the bottom row. Thus, we can see that x is equal to y plus c, which is equal to a plus b plus c. Thus, our multiplier is equal to a plus b plus c, choose a plus b. And converting this to our f function, we see that it's equal to f of c, a plus b. So our claim is that g of a, b, c is equal to f of a, b times f of c, a plus b for all a, b, and c. We can see that f of a, b is equal to a plus b factorial divided by a factorial times b factorial, and f of c, a plus b is equal to a plus b plus c factorial divided by c factorial times a plus b factorial. When we multiply these together, we see that they're equal to a plus b factorial times a plus b plus c factorial divided by a factorial times b factorial times c factorial times a plus b factorial. And cancelling out the a plus b factorial, we're left with just a plus b plus c factorial over a factorial b factorial c factorial, which by definition is equal to g of a, b, c, thus proving our claim. I hope you enjoyed the video, and if you did, leave a like, and consider subscribing for more interesting mathematical oddities.